Today's lesson, we're going to take a look at whether relations or functions are linear or nonlinear. Now, before we go much further, let's just make sure that we understand exactly what I'm talking about when I say a function is linear. Basically, it would mean that if we put it on a graph, the relation would make some sort of straight line. It could be diagonal, it could be perfectly vertical, it could be perfectly horizontal. It could be a negative slope, diagonal going a different way at a very steep slope or a very slight slope. But those would all be linear relationships. And some of those would be functions, some of those would not. The last lesson we learned that we could use a vertical line test to be able to tell if it was a function or not, and I'm not really concerned with that in this lesson. I'm just asking you, does it make a straight line? Is it linear? Or basically it would be, is it some sort of curve? There's the sine curve that we've seen on a few examples. There's also the parabola curves. But you can tell that all of these are curved lines. They're not straight, they're not linear, so we would just put them as nonlinear. So the challenge of this lesson is what do you do when we don't see a graph? What if we just see a relation right here, this set of ordered pairs? Is it linear or is it nonlinear? Well, what we need to do is we need to take the first 2 points that are given to us and plug them into this old slope equation that we used to use for linear equations. So we get 4 minus 2 over 2 minus 0. And let's take just a moment on this first one to remind ourselves of how to do this. This is a y, and this is a y. And I'm just saying this is my second y point, and this is my first y point. So this is y2 minus y1. Our y2 is 4, so it goes right there. And our y1 is 2. So 4 minus 2, and then we come back for our x's. This would be x2, because this is y2. They're together, it's the second point. 2 minus 0. So x2 minus x1, 2 minus 0. And after you work the whole thing out, yes, it does equal 2 over 2, but basically, if you plug that straight into your calculator, it goes ahead and simplifies 2 over 2 to make it positive 1. Sadly, we're not done yet, though. The next thing that we have to do is we have to come through and graph these 2 points right here. I'm sorry, not graph. We need to actually find their slope. So again, we come out and we use the slope formula of 6 minus 4. For those that are a little confused about what I'm doing, I'm now saying this is the second point and this is the first point. So this is y2, this is y1. And then we come back and we say 4 minus 2. So x2 minus x1. 4 minus 2 goes on the bottom. And again, we get 2 over 2, but if we put it in our calculators, that would go ahead and tell us that the slope was 1. Because they have the exact same slope when I checked it the second time with a different set of points, I'm calling it linear. Okay, this relation or function is linear. And let's take a look and see what it looks like if we actually graphed it. Here's my y-axis, here's my x-axis. And let's see, 0, 2 would be about right here. 2, 4 would be a little bit right here. And 4, 6 would be right here. Do you see that it would put them on a straight line? We're not saying we would connect the dots, we're just saying that we could. And so as a result, we know that it is a linear relation. If it's linear, what's the rate of change? What's this mean right here? This rate of change right here is nothing more than slope. The rate of change is another term for slope. So what's the rate of change if it's linear? 1. That's because it's got a constant rate of change. I'd go up 1 and over 1 and wind up right here. Go up 1 and over 1, I'm here. Up 1 and over 1, and I'm right here. And all these points are still on the same line. Let's go take a look at this one. This one's a little bit different. How do we do it? Take a look at these first 2 points right here. So again, we get 2 minus 1 over 4 minus 4. And we get 1 over 0. Your calculators will give you an error message on here because you can't divide anything by 0. We'll talk about this in detail in just a second. Now I come to my second set of points here. I don't give up on this just because I got an error. And I say 5 minus 2 over 4 minus 4. So now I get 3 over 0. They're different, but I just said I can't divide anything by 0. It's going to give me another error message on my calculator. And because I get the same error message, same way that we said because I got the same slope off both of these, I got 1, so we called it linear. Because I got the same error message, I'm going to say it's linear. And what is my rate of change? We would just call it undefined. And that means it's going to be a perfectly vertical line. So let's go graph this one and see if it's true. Let's see, here's 4, 1, here's 4, 2, and here's 4, 5. Do you see that I could connect these 3 points in a straight line if I wanted to? That's why we're calling it linear. It's definitely not a function. It flunks a vertical line test, but it is linear. And if it's linear, what's the rate of change? Well, it's undefined. So that's what it is. It basically means that you can move up or down, but you're not going to be moving left or right at all. Number 3, I think, is where we're going to start feeling a little bit better about the situation. Let's go through and plug in these first 2 points right here. Let's just make it 2 minus 3 over 12 minus 11. And we'd get -1 over 1, or -1. So let's come back through with the second set of points here. You see how I'm just overlapping it? The second point and the first one is going to become the first point in the second set of pairs. 3 minus 2 over 13 minus 12. Well, that's 1 over 1, or +1. They're both 1s, but this is negative. This one's positive. They're not the same. So I'm going to say this is non-linear. It's a non-linear, in this case, function. But let's graph it and see what's happening here. 11.3 is up a little higher. 12.2 is down and to the right of it. And then 13.3 is to the right of that, but up a little higher. So we've got like this V shape. There's no way I can connect these points with a single line. And the reason that I'm doing this test of using the slopes here, remember, the slope of the line tells us how the points connect. Well, right here, when I used these first 2 points right here, it gave us a slope of -1. And that meant I went from the first point down 1 and to the right, and that got me a slope of -1. Then with the second points here, using these 2 right here, this was the first point, this is the second point, there was a slope of +1, which means I go up 1 and to the right. So now suddenly I've got a +1 slope between these 2 points. And because the slopes are different, that's what kept me from being able to run a straight line through all 3 points. And that's the reason I knew instantly, before I ever graphed it up here, that this setup was happening where something was awry. They were not sitting on the same line because my slopes were different. So it's nonlinear. It's not linear, so I don't have to answer what the rate of change is because it's not constant. It's not the same. Number 4 is actually even easier. Is this linear or nonlinear? Remember the definition of a linear equation. Any equation that has 2 variables to the first power. So this is the first variable, the second variable, they're both to the first power, so it is linear. That means that I can graph it and it'll make some sort of straight line. So let's go ahead and call it linear. What is my rate of change? Remember, another word for the rate of change is slope. My slope is always going to be the coefficient in front of x. It's what's multiplying the x. So my slope is +2. In case you're wondering why it's not -6, this would be considered your y-intercept. Where we go graph it, if I put in my y and x-axis, there's my y and x-axis. Here is -6, that is my y-intercept, and I would go up 2 points and over 1 to get my second one. I'd go up 2 more and over 1, and it just keeps building the line out, and that's the reason I know it's linear. And my slope, again, is up 2 and over 1. It's +2 or 2 over 1. That's my rate of change. Same thing as slope. 5, not linear, because it's got that exponent on the variable. We just talked about that in the last problem. This one, think about this for a second. I made a mistake in one of my classes. I let them walk out of here thinking it was nonlinear because they had these exponents, but could we combine like terms? What's 2x squared minus 2x squared? 0. So what's left over? X plus 1, and we still got the y, so it's technically linear. And when we go and graph it, y-intercepts at 1, goes up 1 over 1, up 1 over 1, and it makes just a nice, perfectly straight line. What's my slope, which we're now going to be calling the rate of change for the rest of this video because I'm getting tired of saying slope over and over. It's just positive 1. It's the coefficient in front of your x value. Number 7, handle it the same way we've been doing it in the past. Let's see, 2 minus, oops, let's go back through here. Let's get these two ordered pairs like this. 2 minus negative 5. I'm just saying this is y2 and this would be y1. It's just easier, so I can go 2 minus negative 5. And then negative 1 minus 0. That'll make it 7 over negative 1, which is negative 7. And now, actually let me erase this. Let me go check it again. It's very important that you go through and you always do the second check at least, and I would advise a third if you have like 4 sets of ordered pairs. 0, negative 5, and 1, 2. So it would be negative 5 minus 2 and 0 minus 1. And this will get us negative 7 over negative 1. Negative, negative cancels out and makes it positive. So this is positive 7. This is negative 7. They're not the same. Nonlinear. Here's 8. Grab that third point with the middle point where we use 0, 0 again. Right? And then 0 minus 1. Ooh, positive 6. So you see how they're different again? Nonlinear. Oops. Keep forgetting on that one for some reason. 1 minus 2. Right? And then negative 1 minus 0. Zero divided by negative 1 would be 0. So again, different slopes. Let's just graph this last one just that way you can see it again. Here's negative 1, 1. Here's 0, 2. And then here's 1, 2. And you can see that these are on the same horizontal line, but this one's lower. So I could connect it. Use green here. I could connect these two with a straight line going like that, but it would totally miss this third point. Or I could have connected these 2 points, but it would miss this first point right here. Either way, there's no way you can connect them all with a straight line. It's nonlinear. Don't have to worry about a rate of change as such. Number 10, is this linear or nonlinear? This is not talking about is it a function. That's a totally different question. We would use a vertical line test and we would determine this is a function. Okay? It would pass a vertical line test like we learned in the last lesson, but it's just asking you, is this a straight line? Well, no. Obviously, it's nonlinear. You can see it's all curved. Number 11, we're not asking if this is a function. We're just saying, is it a straight line or is it not a straight line? Is it linear or nonlinear? Absolutely, it's linear. Let's take a look at a couple of points here. Is there any upward change? Are we going up or down to get from this point to this point? No. Is there a horizontal change? Yes, I would go over by 2. What's 0 divided by 2? It's 0. So what's my rate of change? 0. 12, definitely nonlinear. No, it's not a function, but we're not asking that. We're just saying, is this relation, this set of ordered pairs that makes this kind of oval shape, Is it linear or nonlinear? It's not a straight line, it's nonlinear. Here's 13. Linear or nonlinear? Definitely linear. Let's take 2 points and let's determine its slope. It's very, very difficult for me to see, so I'm sure it is for you too. But I think, yeah, I think we've got the best ones. I would move over. Let's call this one 4. So 1, 2, 3, 4. That's a horizontal change of 4, so that goes on the bottom. Remember, our change in x's goes on the bottom, and our change of y's goes on top. And I'm going down, so it's going to be a negative 1, 2, 3, 4, 5. I believe we're looking at a negative 5/4 change. Let's see if this pattern holds out and see if we can go over 4 and down 5 from here to there. 1, 2, 3, 4. No, I've missed it. This is where it gets frustrating. If I give you one of these on the test, I promise you it's going to be easier to see the graph. Here we go. This is actually straight from our book. Let's make it bigger. Let's see. I still believe that this is the point where it hits pretty evenly right here. I'll use this one. That one's getting kind of dicey. Let's see if this holds up. Over to the right, 1, 2, 3. And then from here we go down 1, 2, 3, 4. So down negative 4. Let's try this one. 1, 2, 3. And then down 4. 1, 2, 3, 4. And then let's try it one more time. 1, 2, 3. 1, 2, 3. Yeah, the line's slightly off, but our slope or rate of change is just going to be negative 4/3, and it's definitely linear because it's a straight line. Let's try one more of these that's a little bit easier to see. This time I'll actually put the points right here so you can see where it hits evenly. There we go. So you can use those red dots to tell nice even intersections. You might want to pause the video and after you mention whether this function is linear or nonlinear, figure out what the rate of change and then hit play. Here we go. Linear, straight line. Choose any 2 points. So I'm going to choose this one and this one. I can go up 1, 2, 3 and over 1. So that's 3 over 1 or 3. Let's see if it holds true. 1, 2, 3 over 1. Yes. 1, 2, 3 over 1. Yes. My rate of change is 3.